Hi everyone, my name is Ran and I'm a rising junior student at Yale University, studying mathematics and economics. So today I'm going to talk about the something that I met during my sophomore year, and I think it's really interesting. So I want to share with you guys. It's a bit complicated, so if you have any questions, just raise your hand or just put your question in the chat. I'll try to address them if I can. Sure. I'll share my screen.
In the meantime, participants, please also feel free to send questions to staff members via private message, and then we can relay them to Roger because he will probably not be able to see you during his video presentation.
Yeah, it will be hard to keep track of that. Okay, can you guys see the screen? Yeah, okay. So, yep, this is my presentation. Okay, so today I'm going to talk about tiling with Dominoes, the diamond model, which is the model after this problem. So this is the overview part. I will give a brief introduction to this problem. What are diamonds? Like why we care about that, and I'll provide some simple results like in 2 times n rectangles and 3 times n rectangles. Sorry, someone unmute this. Yeah, please. Okay. So and then I'll give some preliminary definitions like determinant. Some of you may heard this before, but some of you may not. I won't like go too deep into that. I'll just touch on it, and then I'll discuss about some of the general results. It's like we will consider some more complicated cases, but for simplicity, I will just use 3 times 2 rectangles as an example and help you walk through how we derive the theorem. And finally, I will show the dimer models in some other patterns. So here we begin. What is a dimer? Dimer is a molecule or a molecular complex consisting of 2 identical molecules linked together. In another way, it's a polymer with only 2 atoms. So here there's a picture for a dimer. It's some chemical things, and more often it's organic chemistry. Yeah. And a crucial aspect in the thermodynamic prospect of the system of dimers is the number of arrangement of dimers on the lattice without overlapping each other. So I'll keep it simple. Like for example, think about our oxygen. It's O2, right? So it's like we have 2 oxygen atoms and they are connected to each other. Let's think of a space like there are only oxygen in it, and then a question we might think of is like how the oxygen molecules will occupy this space. They have a bond in between and with 2 atoms, and how this type of molecule will occupy the whole space. So this is the general question. But this one is a really, really hard question. So we kind of want to simplify it into some specific graphs. So it's like it's not just a boundless space. We have a bound. Sometimes it's boundless, but it's like we have grids on it, so that we can study it in a simpler way. Okay, so what is a dimer covering? So a dimer covering or perfect matching of a graph is a subset of edges which covers every vertex exactly once. That is, every vertex has a degree of exactly 1 in the subgraph. What it means? It means that we want a collection of the edges in a graph, or like we want the bonds which connects the 2 atoms. Each vertex or the atoms is connected by 1 and only 1 edges. So the problem becomes counting the number of different dimer coverings of a lattice. So it's like in this way we can count how many ways we can put the so-called O2 molecules in the space. So to simplify this, we will only consider quadratic lattice, or we can call it grids. Consider a planar m times n lattice. There are m rows and n columns. Each side at the corners connects to only 2 neighboring sides on the boundary of lattice. Each side on the boundary connects to 3 neighboring sides. And for the interior ones, they connect to 4 in like for all the 4 directions. We can place the dimers on 2 neighboring sides such that each side in the lattice has exactly 1 dimer connected with another side. We can equivalently define this in a grid. So it's like we can think of a chessboard like it's an 8 times 8 rectangle, and then it's like we can place dominoes on it, which is like have size 1 times 2 or 2 times 1. Okay. So here are 2 pictures to give you a better idea of what I'm talking about. So on the left, it's the quadratic lattice. This shows a 6 times 6 quadratic lattice, and here it is a dimer covering for it. So we can see that for each vertex of it, it connects to only 1 edges here. So on the right-hand side, it's the grid I just talked about. So it's like we place 2 times 1 or 1 times 2 dominoes here to cover this grid. And yeah, this is the general idea of the dimer models and how we can apply it in the grids. Okay. So an interesting question to ask is to count how many ways can we tile this. For example, you can imagine you have there's on the floor of your room, we need to tile it with dominoes, and how many ways you can tile it. Yeah, there's a lot of ways, and sometimes it's hard, but I'll start from the really simple cases, like 2 times n rectangles. So I listed the first 5 of them, like 2 times 1, 2 times 2, 2 times 3, 2 times 4, and 2 times 5. Okay, so for the 2 times 1 rectangle, it's a domino itself, and there's only 1 way to put it, just as the grid goes, okay? So we have only 1 way for that. For 2 times 2, we have 2 ways, right? We can put the 2 so first of all, we must have 2 dominoes to tile this, and then we can put both of them vertically or horizontally. So it's like we have 2 different ways. So after that, things got more complicated. So when we put in a 2 times 3 rectangles, it's like we have 3 ways, as I show here. So we can see that we can put 3 vertical ones or 2 horizontals and 1 vertical, and the vertical one can be on the left or on the right. And then here are the 2 times 4 rectangles, and there are 5 of them. Does anyone want to have a guess on how many ways can we tile in a 2 times 5 rectangles? Yeah, I saw number 70. Yeah.
Yes, yeah.
Sorry?
We can budget we can do budget and 2 horizontally on the first row and 2 horizontally on another 2 on the second row and a horizontal rectangle. Then we can get it.
That's a way, but it's like how many ways in total? Do you have any ideas?
Oh, sorry, Chef. Yeah, I think the Chef. I think 4 ways.
4? Okay, some other guesses? Okay, so it's actually 8.
8.
So it's like, yeah, we can see here. So we have, yeah, I'll just show you here. I won't like go through all of them. It's a really long list. So, okay, so we have 8 of them. So does anyone see any patterns from these numbers? I'll recall it again. The first one is 1, second is 2, 3, 5, and 8. Does anyone has a guess? Yep, Fibonacci, I saw it. Yep, so that's a good guess, Joseph. Okay, okay, then we'll have a kind of hypothesis, like it's a Fibonacci sequence. So actually, that's true. It's just a Fibonacci sequence. So the theorem is like for each n, the number of the domino tilings of a 2 times n rectangle is Fibonacci number fn plus 1, where we define it as f1 equals to f2 as 1, and for n at least 3, we have Fn equals to Fn minus 1 plus Fn minus 2. And we can check that F3 is 2, F4 is 3, F5 is 5, and F6 is 8. That's just the corresponds to our tiling. So next, I'll show how to prove this. So I'll prove it with kind of an induction idea. So some of you may heard about this before, but it's like, yeah, I think you will understand it. So we'll first consider 2 of the basic cases. The first one with n equals to 1. As I talked about it, there's only one way to tile the 2 times 1 rectangle. And similarly, when n equals to 2, there are 2 ways to tile it. Okay. So someone asked about Fibonacci numbers. So it's actually defined on here. So it's like F1 equals to F2 equals to 1. And after that, each number is just the sum of the 2 numbers before it. So it's like the third one is 1 plus 1 equals to 2. And then the next one is 1 plus 2 equals to 3. Yeah. Okay. So hope this helps, and you'll learn more about the Fibonacci numbers during the proof. Okay. So then after that, we first addresses the base cases. It's like we consider when n equals to 1 and when n equals to 2. So what's going on when n is larger than 2? So it's like, yeah. So we'll just consider a 2 times n rectangle for some n at least 3. So we are considering those cases. And for the induction, we suppose that all the numbers before it, so it's like for all the numbers that ranges from 1 to n minus 1, we have shown that the number of domino tilings of a such rectangle is just fk plus 1. It means that it satisfies our statement. So for example, if n equals to 3, then we just say that it's like for n equals to 1 or 2, the statement holds. So, and we know that that holds. So that means like if we prove the case for n equals to 3, based on these two, then n equals to 3 also holds. And then after that, we can do this for n equals to 4. If we'll base on the assumption that the statement holds for n equals to 1, 2, and 3. And then we'll see again that based on these assumptions, if n equals to 4 is correct, then we can say that n equals to 4 is correct because we know that n equals to 1, 2, and 3. In these cases, the statement holds. Okay. So there are 2 ways to place the domino covering on the upper left corner of the whole rectangle, right? The first way is to put a vertical domino, and another way is to put a horizontal one. Okay. So in the first way, if we put a vertical one, then the rest of the rectangle, it becomes a rectangle of length n minus 1. And then we know that based on our assumption here, for n minus 1, we know that our statement holds. So how many number of domino tilings can we tile this n times n minus 1 rectangle? We can tile it in fn ways. It means fn minus 1 plus 1. So it's fn, okay? So this is the step here, this part. So there are fn ways to complete such dominoes, okay? And then going back again, a second way to do this is to place a horizontal one here, right? And then after it, we might notice that for the under it, we must place a horizontal domino as well, because otherwise we cannot we cannot cover the lower left corner. So it's like we have to place another horizontal covering. Since if we place a vertical one instead, then it will be overlapping. So we know that we need to cover every cells. So we also need to cover the lower left cell. And we can place a vertical one or horizontal one, but we cannot place the vertical one since this corner is covered by this horizontal domino already. So we are forced to place a horizontal one here. And then what it turns out is that the rest of the rectangle becomes of length n-2. And based on our assumption again, how many domino tiles can we tile that 2 times n-2 rectangles? Someone has a guess? Okay, so here for this part we have n-1 ways. And then we plus these two together. So the total way of tiling the 2 times n rectangle is just the f and n plus 1, which is what we want here in the statement again. So going through it, we can also use the example here. So we can see that for the 2 times 3 rectangles, we can either put a vertical one on the left corner to cover the upper left corner, or a vertical or a horizontal one. If we put a vertical one, then the rest of it becomes a 2 times 2 rectangle. Okay, and then we know that we have 2 ways to place it. So these are the 2 cases on the left. And then the other one is like we have to place we place a horizontal one, and we know that we have to place another horizontal one here. So we have 2 times 1 rectangle left, and we know we have only one way to tile it. So this is the case here. For the 2 times 4 rectangles, that's similarly. It's like for the 3 cases on the left, we can see that it differs from our 2 times 3 rectangle cases by only the left, the dimer on the left or the domino on the left. If we delete this, that's totally the same. And for the right, the two cases on the right, we can just ignore the left 2 times 2, the 2 times 2 rectangle on the left, and then the remaining part is just all the cases we place 2 times 2 rectangle. And this goes on. So this proves that the sequence is actually a Fibonacci number. Does anyone have any questions or no? Okay, good. So those were the really basic cases for the 2 times n rectangles. And how about 3 times n? It's slightly more complicated, and I won't go into details because it's really hard to explain. But the general idea is that there are basically 4 patterns here that they kind of go from one to each other to another. So for example, for the gray part, that means we have filled them with dominoes already, and then we think about to place another domino on the right part on the right. And then if we place a vertical domino on the right, then we come to the pattern at the lower left corner. On the other hand, if we place a horizontal one, it comes to the upper right corner. That's the other case. So you can check this, and we can see that these 4 patterns actually goes in these directions, and we need some more advanced calculation techniques to do this calculation. Okay. So those 2 are just kind of the easy cases. It's like we still know it's like 2 times n or 3 times n. What about m times n? The more general cases, we have no idea because we don't know how large m is, and we have no idea. We have totally no information about that. So how can we tell, like, how many ways can we tell it? So we see that the method we are using we cannot use this method again for the higher cases. So we need to find some other ways to do it. So I'll introduce an idea that is taught in college, but it's like I will keep it really simple, so you guys can understand it. So it is called determinant. But before that, we have a matrix. A matrix is a kind of a rectangle of numbers. So it's like for all these numbers here on the upper left corner, it's inside the parenthesis. It's like they are all numbers. We just put the real numbers here, okay? Just like 1, 2, or 0.5 or 1.6 and some other numbers, okay? So here we have n rows and n columns of numbers in this matrix. We call it matrix. And then the determinant of that is defined in this way. So this is the formal definition of it, but don't worry, I don't expect you to know about that. And I don't expect you to understand what this formula says. So I do hope you guys can understand the base cases for 2 times 2 and 3 times 3 determinants. So for 2 times 2, the determinant is calculated in this way. So if we have 4 numbers like A, B, C, and D in this way, then the determinant of this matrix is A times D minus B times C. So this gives you a number, okay? So further, for the 3 times 3 cases, the determinant is calculated in this way. So we just we pick the first row first of all. So it's like A, B, and C, and then we alternate the signs here. So for A, we use plus sign before it. For B, we use minus, and for C, we use plus again. And after it, we multiply it with another determinant of a smaller matrix. So how do we get the smaller matrix? For the case of A, we'll delete the first row and delete the first column. And then the remaining part, as you can see here, we have E, F, H, I, and that's the matrix here. So for the determinant of 3 times 3, we just put this term here, A times the determinant of this smaller matrix. And then for the term with B, we'll just delete the first row and the second column where B is in. So the remaining part is D, F, G, and I. And this is how we get this matrix. And then similarly for C, we delete the first row and the third column to get this smaller matrix. And again, we apply the determinant to these 2 times 2 matrices, and we know about how to calculate these things. And the final way is this one, this expression. So it's like A times E times I. There's an easy way to remember it. Like first way, you do all the pluses with going in this direction. So it's like going to the right bottom right. A, E, I, this is the first term. B, F, sorry, this is the typo. B, F, G here. B, F, and then you go back to here, G. Then the third term is C, D, H. And then for the minus terms, you go the other way, go the down left direction. So your minus goes C, E, G, B, D, and then here I, and finally A, F, H. Okay, so this is how you calculate determinants. Does anyone have any questions about it? It's something really new, but I hope you can understand it. Okay, Joseph has a question. So for any matrix, this formula splits it down into smaller matrices, then into even smaller matrices until it reaches the 2 times 2 matrix, which we can compute. Yes, that's correct. That's the general rule. It applies for even bigger ones like 4 times 4. That's the same rule. We will have like A, B, C, D here, and we'll change the names here. But anyway, A, B, C, D here, and then you will see terms like A times the determinant of a smaller matrix minus B times a smaller matrix plus C times something and minus D times something. And this rule applies always. And then you can make it smaller and smaller. Finally, you can compute it. And this is actually what this formula tells, just to say in another way, a simpler way so that we can understand. Okay, any other questions? Okay, so before going to the next page, I just want to emphasize again that first of all, we see that there are alternating signs, so we switch the signs, and it's not always plus. We might face minus. This is the first thing you might keep in mind, and the second thing is that if we look at it, each term, remember there's a typo, it should be B, F, G. We can see that each term here, for the 3 times 3 cases, we just simplify it, okay? So we can see that each term is the multiplication of 3 terms in the matrix. And for these 3 terms, they all are in different rows and in different columns. So for example, the term A, E, I here, A is in the first, or I'll just pick a random one, maybe C, D, H. So C is in the first row, D second row, H third row. And for the columns, C is in the third column, D the first column, and H the second column. This is a really important property that you might want to remember. And I'll kind of revisit this again when we talk about the more general case for the domino tilings, okay? So, okay, we'll go next to the dimer covering. So remember in our simple result, we try to tile the 2 times 3 rectangle or 3 times 2, that's totally the same. You just rotate it by 90 degrees, and then that's totally the same thing. So we know that we have 3 different diamond coverings for 3 times 2 rectangles, as it's shown here. So we want to do some, I'll introduce, like, first of all, we want to label all the cells. So I'll just keep in a simple way. So 1, 2, 3, 4, 5, 6. Okay, we'll label this. And another thing is that I want to introduce an idea of coloring. So we can actually color this grid, all the grids, by only 2 colors, black and white, like how the chessboard did, right? You remember the chessboard like goes black, white, they alternate the colors. So here we can also do the same thing to this grid. So we can, for example, we'll color the cell 1, 4, and 5 black, and then 2, 3, and 6 white. In this way, for all the pairs of adjacent cells, one of them is black and one of them is white. Okay. Okay, so then I'll introduce an idea of adjacency matrix. I put a quote mark because it's not the actual adjacency matrix. I'll just use this word here because it kind of describes this idea. Okay, so in this matrix, what we do is like we'll put the black cells on one side and put the white cells on the other side. Okay, so we put, yeah, you can switch the order. That's totally fine. But it's like this is the general idea. So we'll put like 1, 4, 5 here in this row as the indices of the rows, the columns, and similarly put the white ones 2, 3, and 6 here as the indices of rows. Okay, and then we will put like 1 or 0 in this matrix. Okay, so it's like if it's like for example, let's take the first row and the first column. So indexed by 1 and 2 separately. Okay, so for 1 and 2, it's like we can see 1 and 2 are adjacent in this grid. So it's like they share an edge. We can definitely tell it, right? So in this case, we put a 1 here. So if they are adjacent, we put a 1. On the other hand, if they are not adjacent, we put a 0. So for example, here, the case indexed by 2 and 5, we can see we put a 0, and actually 2 and 5 are not connected. They are not adjacent. They do not share an edge. Okay, so in this way, we form this adjacency matrix, and you can check that it is actually the case. So we have 7 pairs of adjacent cells, and here in this matrix we also have 7 ones. So someone may be curious, like, what if, like, for example, why we put whites here on one side and the blacks on the other? Because the only pairs of adjacent cells, one of them is black and one of them is white. We would never face a case where the pair is both of them are white or black. We never face that. So this kind of explains the adjacency matrix here. Okay. So does anyone have any questions on this adjacency matrix? How we kind of form it? No? Okay, I'll continue. So after that, we'll try to consider like use the determinant here. And we'll see that it's like here we got the answer is -1. But it's like, remember that we have 3, the answer for the different dimer coverings or domino tilings is actually 3. And here we have three terms, 3 non-zero terms, and all of them are actually 1 or -1. Okay, so the term here, here, and here. Okay, so for the other 3, it's 0. So why we need to use the adjacency matrix with the determinant? So anyone has any guesses? You may raise your hand.
If you have any questions, please also just private message staff, just to make sure we don't have audio colliding in the middle of the lecture.
Okay. Okay, never mind. I'll just like talk about why we do this. Okay, so first of all, the terms in the calculation of the determinant give all the configurations of pairing between the black cells and the white ones. What does it mean? So it's like for a term in the determinant, for example, we just say the CDH term here. So here it is the 0, 1, and 1 here. 0 is indexed by 2 and 5, a white and a black. 1 is indexed by 3 and 1, white and black, and 1 again here is indexed by 6 and 4, white and black. So we have 3 white cells, and 3 black ones. So we kind of pair these so that we can make 3 pairs. This is what this means. So when we have a 0 in a single term, it means that this configuration of pairing does not work, i.e. there is at least a pair of black and white cells that are not adjacent, as in this case, the so-called CDH term here, 0, 1, 1. We have 0 here, which means that 2 and 5 are not adjacent. That means it's not a valid domino tiling. If we face the cases where there's all ones, for example, 1, 2, 3, and 4, and 5, 6. So this on the diagonal. So this we can see that it actually pairs the 1, 2, 3, and 4, and 5, 6, and all of these pairs are adjacent. So that's a valid one. Each non-zero term, which are the valid ones, has absolute value 1, and the number of non-zero terms in the calculation is exactly the number, singular, of the dimer coverings. So this is why we are interested in this way, we kind of perform the pairing for all possible ways between blacks and whites. And then among them, we try to see like which pairing is works. So all the non-zero terms here with absolute value 1, which means it's either 1 or -1, is a valid pairing. So this counts the number of domino tilings. Okay. So what is the problem for this version of adjacency matrix? I talked about it. It is because of the signs. So before I said that the signs is alternating. So it's like we have pluses and minuses. But here, because of this property, we cannot count the correct value. That's the reason. So we have to tackle this problem. We need to deal with it. So here we introduce a more advanced version. It's called small Castellane matrix. So to correct the signs, we put I, the imaginary unit, on the vertical edges here. If we put the horizontal, if we have like an even number of columns, then we put the i's on the vertical edges. We put this as the weight of these edges. I is defined by I, the square of I is -1. So it might be a new idea for you guys, but just to remember this, that's all you need to know. The square of I is -1. Okay, so we put weights on these vertical edges or vertical dominoes. And then we update our adjacency matrix and we get our small Castellane matrix. For example, we can see the one indexed by 2 and 4 corresponds to this one here. It's a vertical edge or the vertical domino here. So we put an I on it, and similarly for the other ones. For the horizontal ones, we still put 1 there, okay? So we get this updated small Castellane matrix, and then we do the calculation again. And we are surprised to see that the result is actually correct. It's 3. So it's like for this term, it's 1. These 3, those are 0, so never mind, it's just the 0. For these 2 terms, those are -I squared, which is -1, which is +1. So altogether, it's 3. So this, by putting the imaginary units on the vertical edges, we deal this problem. So you might be wonder why that's the case. The reason behind it has to do with the property of the determinant. The method, but it's like this is something really advanced that you might learn in college. So it's like I want like also it's like you'll probably spend a semester on it to come to this conclusion. So it's like I'll just leave it there. Okay, just trust me. We'll just put eyes on the vertical dominoes, and that's how we deal with it. The method also applies to larger matrices. So I'll show the case for 4 times 2 rectangle, and you may help me. So again, here's the 4 times 2 rectangle, and we label the last row as 7 and 8. And again, we updated the indices here, and we update our small Castellane matrix. So after that, we just calculate the determinant here. Okay, so as Joseph just mentioned, it's like for the 4 times 4, we have the same formula. I only keep the first 2 terms here because the other 2 starts with 0. So it's actually 0. So we don't have to care about that. Okay. So here is this one. So does anyone have any idea about what the answer is? You may put in the chat or like raise your hand. A hint, this one is just the matrix we had previously. The answer to this is 3. Yeah, I will give you some minutes. So anyone comes out the result? Okay, never mind if you did not calculate it out at this time. If it's a test, you will have a long time to do it. As Professor Lam just said, it's like you have a week. Never mind. So I'll just do the calculation for you. Okay, so for this part is 3, 1 times 3. We know about that. And then for this part is I times this determinant. We'll see that there are only 2 terms that work. This term here, I, 1, 1, give a product of I, and another term I, 3 I's. So it's like the I square, and then this is actually minus I. But for this term, we have a minus sign. So altogether, this gives 2I. So altogether, 3 minus I times 2I. So this gives us 2I squared. So minus 2I squared. I squared is minus 1 again. So we get 3 plus 2 equals to 5. Okay. Okay. So this is how we calculate for this one. And compared to what we had previously, I don't know where it is, but it's like for the 2 times 4 rectangles, we actually have 5 ways. We have proved it. Okay. So the mathematicians also did something similar, and then with great calculation, but helped with linear algebra and some more advanced things, you don't have to know about it. And here it is, the theorem here. So it's a really complicated formula, and it's okay. But it's like it's way simpler than I would expect it be to calculate these sort of questions. And how about the case for a chessboard or like an 8 times 8 rectangle? And you can use this formula here to calculate it, and the answer would be this. So I won't read it. It's over is over 10 million. So that's really a big number. And if you are trying to enumerate all the possible ways, it means that you probably cannot do it. Okay, so never try that. So yeah, and finally, I'll just show you some great pictures, like discuss the diamond model in some other patterns. For example, so the bottom, the lower left corner is still in the grid, but it's like here we have a larger grid. So this is just a domino tiling for that. For on the other cases, we have this hexagon. The regular hexagon is like we can also use this kind of tiles to tile it, and it's also a dimer tiling, as you can see here. We also can tile triangles, and here this one is a really interesting one. So it's like you kind of view the triangle here as like a three-dimensional pattern. You can kind of imagine it, and then you just flip it and rotate it so that it's flat here, and then you will kind of see the heights here. This comes out of this triangle ones, and you can actually do the same thing for the hexagon ones. And there's a lot of really interesting properties behind this, but it's like really complicated, so I will never talk about this. Okay, so this is the end of my presentation, and here are the references. Those are really great papers and really hard ones, and if you're interested in this, like you may take a class in the college and explore this kind of fascinating ideas. Okay, thank you guys.